Good morning, everyone. I think have concluded that nice sunny days at Empire Farm Days are preferable over rainy days. I remember last year giving a presentation, and this roof here, this metal roof, was not very friendly when it's pouring rain. It was really noisy. Anyway, so I hope I will be able to kind of maybe give you a little bit different perspective around soil health. And we've been talking about it now for quite a few years. And we've been, looking at some of the data that we've collected, and I hope you enjoy that. I'll also go a little bit into the history and the geography, and I should recognize Joseph, who just introduced me, that he's made a big contribution to this in terms of the data analysis. So, now this is probably something that you're familiar with. We humans, animals too, are impacted by soil health through multiple pathways. One, of course, that many of you are interested in is sort of the agriculture food pathway. The other one is sort of what we might call the other ecosystem services, things like water quality, air quality, etc. And so they impact us from both sides, so therefore people should be very interested in soil health. Today, I also want to kind of provide a perspective on how us humans in turn are impacting soil health. So soil health impacts us, but we are also obviously having a big impact on soil health, positive and negative. So let me go back to very, very basic level of what are soils all about and how do they develop. Right, so what are the basic ingredients of soil? What are soils made up of? How do they develop? Basically minerals, water, air, organisms, and the sun. So minerals are the particles. Water dissolves some of these minerals to make the nutrients available. Air exchange is important to keep things aerobic and also to facilitate plant growth and then in turn other organisms. And of course the sun is needed because of photosynthesis. And so the plants capture the energy and the nutrients and build the soil over time, right? So most of our soils here, we might say, are maybe about 10, 12,000 years old because we had glaciers here at that time. So what we see is building up in the soil is about that time period, okay? So on the left here you see a grassland soil. You may be thinking about Iowa, Illinois, Nebraska, places like that, where you have deeper rooting, and we tend to see more buildup of organic matter. That's what grassland soils do. On the right, you see a forest soil, which is more from around here, where most of the buildup of carbon and nutrients is through leaf litter that then gets incorporated into the soil. But most of that stays more into the surface, while in the grassland soils, we see the big buildup. So the way you can look at this is this carbon and nutrients and water that's being held in the soil. It's like a storage reservoir. A storage reservoir for us to grow crops or for animals to live or whatever, okay? So I'm just going to show you some data here from a study from quite a while ago, actually, that shows you how much carbon and phosphorus, I'm just looking at one nutrient, that gets built up in the soil, in the natural soil. And these numbers probably don't mean anything to you, but you might say, you have in a soil here in Indiana approximately 3,000 pounds of phosphorus per acre in the top 12 inches. How much is that? Well, that would be, if you were to grow corn year after year after year and you would harvest everything and you would move it away, you could do that for about 80 or 100 years and then you run out. So that's kind of the storage reservoir that the soil provides, okay? So when we start to develop new agricultural land, and we don't do anything to kind of maintain that fertility, you got about 100 years. That's it. All right. So we have to manage the soil so that we can maintain the carbon and the nutrients. So that's the natural soil, and of course we have started to develop this natural land into agricultural land. So we till the soil. It stimulates the decomposition of organic matter. The good thing is it makes all those nutrients available so we can grow crops, but we're also drawing down on our bank account, right? So we're drawing down the nutrients that were accumulated in the soil over a period of 10,000 years. Now we say, okay, we're going to be using it to grow our crops, right? And so if we don't replace those nutrients with fertilizers, we run out, right? Again, 80 to 100 years. Also, when we till the soil, we reduce the strength of the aggregates. We break the structure of the soil down. So this then promotes erosion and all kinds of other problems. And this tends to happen more quickly in forested land than in grassland, right? A lot of our land in New York, we used to have 80% of our land outside the Adirondacks, 80% of the land was agricultural land, right? If you go to the southern tier now, most of it is in forest because it was no longer profitable, was no longer good land to farm. All right, so agriculture soils are also less efficient in capturing the solar energy and the nutrients in the soil. Think about growing corn, right? Especially this year was kind of a late year because of the wetness. The plants didn't really start to accumulate biomass until the middle or end of June, right? And if you had a natural vegetation, as soon as things warm up in the spring and the sun comes out, you start to accumulate carbon and nutrients. Okay, so an agricultural system kind of challenges this bank account idea. And in addition to that, and I'll come back to that later, we tend to remove a lot of the nutrients because we harvest our crops. If we don't recycle them, then we remove those nutrients off the land and they go somewhere else. All right. We do partially recycle some of them, typically through residues or manure. So the outcome of that is that there's sort of a net depletion of soils. And that means that our soil health goes down unless we do something about it, unless we use practices that really reduce those losses. Okay, just to put that in a picture. So on the left here, you have a natural system, or maybe like an old style farming where you have an integration of the livestock and the crops. And then most of the carbon and nutrients gets recycled, right? A little bit gets removed. Maybe it gets removed as some of the crops, or maybe the milk gets removed off the land and doesn't get recycled. But most of it gets recycled, as opposed to, say, a cash grain operation, say corn and soybean operation here in New York, or maybe in Iowa, or places like that. You basically harvest about 60 to 70% of the carbon and nutrients. You take that off the land, and so you recycle much less of the carbon and nutrients. So you need to make up for that some way or another. Well, we do that through fertilizers. The nutrients we can replenish, but the carbon doesn't get replenished, right? So most of the carbon gets removed. So hence, this little worm is a little happier than this worm. Okay, it's not as favorable of an environment. And when we do a lot of tillage, we burn up even more of that carbon as carbon dioxide, and we may lose it through erosion as well. Right? So this is a much more challenging system, and I'll come back to that when we started to analyze some of our data of how, say, a livestock farm, a dairy farm maybe, compares to a cash grain operation. Okay, so that brings us to the concept of soil health. Right, so everybody here probably has some idea what we mean with soil health. The way I kind of emphasize it is that with soil health we emphasize the human, the anthropogenic impact on the soils. Okay, and we look at it from a more multifaceted perspective, looking at the physical, the chemical, and the biological processes in the soil. Right, so we may look at soil quality and the quality of the soil as it naturally developed, right? And then on top of that, we can say, well, what's the impact of how we have managed that soil? If we managed it well, then we may have a really nice soil. If we didn't manage it well, then the soil health will have gone down, right? So conceptually, why are we talking about soil health? Because we see that this anthropogenic, this human management, is becoming a big factor in terms of the quality of the soil, right? Does that make sense? The other thing is that we've tended to, over the past 50 years, put a lot of emphasis on the chemical functions in the soil, the chemical properties. How much phosphorus, how much potassium, what's the pH? And we now recognize that we really need to look at it in a much more holistic way, especially the biological component of the soil, right? So because we know that the physics and the biology and the chemistry impact each other, they interact, all right? For example, if you have a physically degraded soil, like a very compacted soil, it doesn't drain well, it's very hard, well, then the biological processes like plants growing or earthworms being in the soil is compromised, right? So poor physical condition impacts the biological condition, but it can also work out vice versa. If you have, say, use a cover crop, you improve the biology of the soil, and that then improves the structure and reduce the compaction level of the soil. So they all interact, right? A soil with a very low pH tends to have rooting problems, right? So chemistry impacts biology, right? So that's the main point here. We're not just looking at the chemistry anymore. We have a much broader perspective. And that kind of follows the way we think about ourselves and the human health. We have a more holistic perspective on that now. We're not thinking about, oh, I have a disease, let me just take a pill. We think about, how can I holistically change my lifestyle, right? How can I manage myself, you might say. Okay, so that's kind of an introduction. The other thing that I want to talk about a little bit is the spatial interconnections. So we tend to think of soil health as something that's in place or in situ, right? So can you improve the soil health in this location, right? But there's actually a lot of spatial dimension to this, right? So there are areas in the landscape that are areas what we call convergence or confluence, where actually soil health, typically also water, kind of comes together, like in valleys, okay? And there are other areas in the landscape, typically in the upper parts, that tend to lose the health, that tend to lose the carbon and the nitrogen through, say, erosion or leaching of nutrients, okay? And a lot of times we haven't really considered that. But when you look at it from a historical perspective, it's quite obvious how important these spatial processes are, right? We have these processes happening naturally, sort of erosion, sedimentation, and leaching, but we also now increasingly have this human component, the anthropogenic processes, that starting to greatly impact the health of the soil in different parts of the landscape, in different parts of the state, in different parts of the country, in different parts of the world. Okay, I'll try to illustrate that. So one classic example that you're all familiar with from your middle school history is the Nile Valley, right? Thousands of years of continued crop production prior to the fertilizer age. Why was that? Well, the Nile River is a huge basin, goes all the way from the Mediterranean, all the way into East Central Africa, Kenya, places like that. And so you have a little bit of erosion from this large river basin kind of comes together in these streams, in the Blue Nile and the White Nile. And then, as you remember from your history, the sedimentation builds up, and you have this little bit of sediment, a little bit of carbon that gets added every year, but it allowed the Egyptians to grow crops there for many, many thousands of years, continuously. How is that possible unless you have some source of carbon and nutrients, okay? So here is, what maybe an area in Ethiopia looks like. Then that sediment and carbon and nutrients ends up in the Nile. This is where the Blue Nile and the White Nile come together. You see here the floodplain, and then you here have the delta. Okay, so these are areas of confluence. This is where the nutrients and the carbon historically came together. Another great example of that is central Mexico. This is the area where the Mexica culture, or the Aztec culture, was located. There's this huge lake in central Mexico that no longer exists. You know where this is now? Mexico City. It's all been drained. But this area, this natural lake, was fed by streams from volcanic areas around the lake. And so they had this continuous stream of carbon and nutrients coming And so people were able to develop civilizations, grow crops year after year after year, because they have this natural fertilization, okay? In the surrounding areas, of course, that was not a good area to grow these crops. So in this area, you have these wonderful organic soils, marshy soils that build up, very productive. The Aztecs built these huge cities right in the lake, right where they had all the nutrients and the carbon available, okay? And so they developed this raised field, they call them chinampas, maize, bean, and squash, as you know, the traditional crops in the Americas, and it became a center of food production and trade and the arts. But it started by being in the right locations so that you could grow crops year after year after year without having to worry about the soil depleting because it was being replenished. Okay? Interestingly enough, too, these people were the original no-tillers. They didn't plow the land. They used planting sticks, and they planted their corn and their beans. They didn't do full season plowing or full width plowing until the Spanish invaders came and said, "Oh, you guys are so stupid. You don't know how to grow crops. You have to plow the soil." Well, we all know that the history of that, right? But now we say, like, these guys were really smart, right? Because they were the original no-tillers. Okay, some other notable areas: the Indo-Gangetic Plain here in northern India and Pakistan. Thousands of years of continued crop production without fertilizer. Why? Because here's the Himalayan mountains, and they had this constant flow of sediment, carbon, and nutrients, flooding the valley on an annual basis, and therefore having the ability to produce. North China Plain, huge area. Okay, similar thing, the Yellow River. Why is it called the Yellow River? Because it had a lot of sediment. It flooded these areas continuously so you could grow crops. So what have we done now? Of course, we control the flooding. So this is no longer happening. The other thing that's happening is these two areas, these two plains, are the most urbanized in the world. There's about 2 billion people work, between these two. There's about 2 billion people that live here. So some of this most productive land has become urbanized. How about New York? Where are the most productive soils in New York? You find them in the valleys. This is the Genesee Valley. Anybody here from the Genesee Valley? You'd be lucky if you have land there because that's the most productive land. Farmers in the Genesee Valley or other valleys, Schoharie Valley or whatever, they attain yields that are often higher than what you might see in places like Iowa. Okay? Why? Because it's these confluence areas, and so there's sediment in the valley, and there's a lot of carbon because it's been building up year after year. Okay? So that's why the spatial connections are so important. Here's another example. Where were most of the Cayuga tribe settlements? Okay, this is we're about here right now, Empire Farm Days. Most of the settlements were in the valleys right by the lake. Right, those are the most productive areas. You had the water, you had the nutrients, you had everything. Okay, so when you think about how some of these more ancient cultures, where they chose to live and grow their crops, it was typically in these areas of confluence. All right, so areas of confluence, but there's other areas that are losing, of course, the carbon and the nutrients and the soil health. So way back, maybe say even in biblical times, those areas would be pastures. You wouldn't be growing crops there. Right? It was unproductive land. As soon as you started to grow crops, because these were often hilly lands, you started to have serious erosion and the soil depleted. Right? So it wasn't until somewhat later when humans really started to farm these areas because we had to. We had growing populations, but those areas were the most subjected to erosion and loss of the carbon and the nutrients. Right? So we need to manage these areas very carefully. Most agricultural land is in these areas of divergence. They tend to lose the nutrients through leaching and erosion if you don't carefully manage it. Right? So that's why we have to use practices like no-till and cover cropping and things like that. Because naturally, these areas tend to lose those. Okay, so those are sort of the more natural processes. How about the anthropogenic? How about the human spatial reallocation? Right? Any field in New York or anywhere else gets carbon and nutrients from somewhere else, or they're exporting it to somewhere else. All right? So a classic example of that is a modern organic farm. You know, modern organic farms, almost all of them need to use compost or some other kind of nutrient and carbon source to maintain their fertility. So most farmers, most organic farmers, end up using something like compost, or they're bringing in manure or something like that. So what they're doing is they're taking these carbon and nutrients from a larger area, sometimes even an urban area where maybe leaves or other waste have been composted, and they're bringing them onto their farm. So there's a spatial reallocation, a concentration of the carbon and nutrients that goes onto these organic farms. And that's a good thing. We're using some of the excess carbon and nutrients that you might see in urban areas because of urban leaves or whatever, or other waste materials, food scraps and all that. And we're saying, we're gonna be reusing that, and we're gonna bring that onto a farm where that can be used to grow crops. Right, so there's a spatial reallocation of these resources. And that's human ingenuity in a way. And we could probably do much better that way. All right. So, because what has happened is that over time, we used to have these integrated crop and livestock and human farming systems. So, the farmer grew the crops, and raised the animals that were fed by the crops. The nutrients were recycled, the carbon was recycled, and mostly it fed the farm family. With urbanizing societies, we started to separate the humans from the farms. And even though most of the farms, say in the 1800s, were integrated crop livestock farms, some of those nutrients and carbon ended up in the cities. Now we have more of a system where often the primary production of crops is separated from the animals and separated from the humans. So this cycling of carbon and nutrients is compromised. I'm not saying it's not happening, but it's less than perfect. Okay? And I'll try to illustrate that. Think of the US corn belt, the corn and soybean belt. Right? So a lot of fields, even though there is quite a bit of animal agriculture there, most of it is cash grain operations, and the grains, mostly corn and soybeans, end up being shipped to other parts of the country. So for example, here in New York, with a lot of our dairy farms, we tend to be a net importer of these grains and therefore carbon and nutrients. Okay? A lot of it goes to Idaho, a lot of dairy in Idaho, California, hogs in North Carolina and Virginia, places like that. Right? So they are, even though they're growing crops there, they're also importing a lot of that grain. And so this, in a way, kind of creates problems on both ends, because we have a little too much of those nutrients and it's creating a problem here. Now, you might say, in this area that's the main grain producing area, we're making up for that deficit through fertilizers, right? So we're bringing phosphorus from Florida, the Carolinas, Idaho, places like that, and so we can replenish the nutrients. But what we're not replenishing is the carbon. The carbon does not get replenished, right? So the grains get exported out of these regions. We're bringing the nutrients back, we're not bringing the carbon back, right? So what we're now seeing is that these soils in the main grain-producing areas, they don't look so good, okay? And at the same time, because we're taking the carbon and the nutrients from one place, and we're trying to concentrate them in these livestock-oriented production areas, we're in one of them, right? And it tends to be a problem. We have too many nutrients. You know, most of the livestock farms in New York are kind of high in phosphorus, kind of high in potassium, and so we're concerned about that with our freshwater lakes and all that. And there's other parts of the country where that also plays out. All right, so we're doing the spatial reallocation of the carbon and the nutrients. We're reducing the soil health in the area of export, and we're increasing the soil health in those other areas. But it's also creating excess problems with, especially with nutrients. So here's a soil health test report, and I'll come back to that later. From a typical USA grain farm, this is a sample that we analyzed in our lab. And on the right, you see a dairy farm from New York. And typically, basically green is better. And we see that the dairy farm has, everything, low hardness, high aggregate stability, high organic matter, looks really quite good, except for phosphorus because it got a very low rating because there's too much phosphorus, right? So we downgrade that. But you can see that the typical grain farm from, I think this one was from Iowa, it has a lot of problems because it hasn't had this natural cycling of nutrients and carbon. All right. So now this is happening also at the global level, right? Even yesterday's news was about the Chinese not wanting to buy soybeans, right, from us. And so this is a global problem, right? Because you know how much of the pigs in the world live in China? You make an estimate. Anybody? 50%. 50% of the pigs in the world live in China. They are raised in China, right? China is not growing the soybeans and the corn to feed these pigs themselves. They're importing them from us and from Brazil and Argentina primarily. Okay, so this here shows the flows of grain. This is soybean, this is corn, a lot of corn going to dairy farms in Japan as well. And so the Americas are basically exporting grain, primarily corn and soybeans, and it goes to other countries, especially China. All right, so, but the way I want you to look at that is we're also exporting soil health because we're exporting the carbon and the nutrients that keep our soils healthy. Right, so this is a global phenomenon. So we should be raising those pigs here in this country and recycle the carbon and the nutrients through the manure rather than shipping all the grain to China. That would be a much more sustainable way of doing it. But this is where we are. Isn't that a fascinating map? How much the Americas are basically supporting agriculture, especially animal agriculture, in other parts of the world, Europe and Asia especially. Okay, so we are exporting the ingredients of soil health from much of our agricultural land here. Okay. This is a dairy farm in Japan that I visited last year because one of my former students is works at the university there. And you visit this dairy farm and you look, and I think they maybe had 200 cows, and they had only very little land. And so how can they do that? Well, they're importing most of the feed, right? So that's how that happens. Okay, let's talk a little bit about soil health measurements and soil health assessment, which has been a focus of our work for actually almost 20 years now. We decided that it was important to put numbers to soil health. If you don't measure it, you can't really manage it. We've been doing it with traditional soil testing for years. It's a huge success story. Farmers know how to manage the phosphorus and the potassium and the pH very well. They know how to interpret the numbers and all that. But the soil biology and the soil physics, nobody really was measuring that. Okay? So just to give you a little bit of a sense of our conceptual thinking, so soils provide services to us, like food production or water quality protection. And those are supported by functions, like plant growth support or biota habitat. And that's supported by processes and properties and indicators. So what we do is we measure those properties. And so when we do that, we can then in turn say something about the processes, the functions, and the services, right? By measuring something, you can take it back to what that means in terms of, in our case, growing crops. that's the idea. And we do that in this more holistic way by not just looking at the chemistry, but also the biology and the physics. So this is the front page of a soil health test report. We've been offering this for quite a few years now. Measured 15 indicators. There's physical indicators, hardness, the water retention capacity of the soil, how stable are the aggregates of the soil, very important indicator. Biological indicators, organic matter, protein, respiration, carbon, and then the classic physical indicators. Now this is a fairly typical report that we've seen. So again, look at these colors. So we are measuring and we're giving the client the values, and then we're interpreting those numbers and we give them a color. So green is good, red is bad, and then we have those intermediate colors. So when you look at this report, so where do we see most of the green? We see it at the bottom here, the chemical indicators. Why are they all scoring 100? Because the farmers know how to manage the chemical indicators. They've done it for decades. They never looked at the compaction levels or the biology. Okay, so that's what we're doing. We're expanding the way we look at the soil. So here are these indicators. They're kind of linked to processes. So chemical indicators is kind of the standard test. So nutrients, pH, salts, or heavy metals, if that's a particular concern. The physical indicators, aggregate stability, really, really good indicator of the physical quality of the soil. You know, how crummy and how strong those crumbs are. This is available water capacity, basically how well the soil acts as a sponge, how well can it hold water, okay? And then we measure the hardness of the soil, or the penetration resistance. So they all relate to important processes for either agriculture or urban or other uses. So here are the biological properties. So we do 4. Organic matter, and then basically indicators of the quality of the organic matter. So what we're saying, it's kind of like looking at food, right? You have a hamburger or you have a salad or something like that. And you might say, well, how much is carbohydrates? How much is protein? How much is vitamins, right? So in our case, we're looking at the total organic matter. Think of it as the total calories of your meal. And then how much of it is proteins? How much of it is what we call active carbon, that's part of the biological system, that's being turned over. And then respiration is basically how well does the soil breathe? How well does it exchange, kind of like us breathing, right? That's kind of a good indicator. A lot of times when you do your physical, you'll do a test like that. So this is important. This is really a new component. It's to recognize that yes, we may have 4% organic matter in a particular soil, but the amount of protein can vary by a factor 3. In this case, between 5 and 15. Right? So not all organic matter is created equal. Some of it is higher quality, some of it is lower quality. If you have more protein, it means you also have more nitrogen. You have a more healthy biological system. It is the same with a meal. If it's just carbos, or that's not as good as having carbos and protein. Okay? That's the idea. So, and then the soil health test report is basically 10 pages. I won't go into details. And then we give a set of recommendations with that. Okay, that's the basic idea of these soil health test reports. I won't go over that this time. We've done it in the past, and you'll probably get a chance to hear it as well. But it's targeted towards what is the problem. If your protein level is low, probably you need to bring a legume into your system, okay? Because legumes have more protein. If you have a compaction problem, maybe you need to think about an aggressive rooting system of a cover crop. Things like that, okay? So we can target things quite well. Right, a little bit of our research results. So we have a lot of data on soil health because we've been measuring it for a while. So one study that we did actually just across the lake at the Musgrave Farm in Aurora, New York, we were interested in seeing in a long-term trial what's the beneficial effect of no-till over plowing? Okay, we kind of assume that over time you see an improvement of soil health with no-till. We hope, right? How about a cover crop? Well, typically with a cover crop, you have an injection of a lot of sort of fresh organic matter, active rooting and all that. We tend to see a quicker response in soil health. One of our questions was, what happens when you combine those two? Right? Do you get this? Do you get initially mostly the benefits of the cover crop, and then over time, maybe after 3 to 5 years, you get the benefits of the no-till on top of that? You know, is it additive? Does it become all in all better? And so, first we're looking at the no-till versus plow-till, and we see that with these indicators, aggregate stability, active carbon, protein, and the other ones too, we really do see a very positive response. No-till makes the soil healthier in terms of our indicators. And you see here, aggregate stability goes up by 92%. Pretty significant. So if we combine 20 years of no-till and plow-till with 3 years of cover crops or not, we see that there's a small additive effect. So this is plow-till, no cover crop, plow-till with the cover crop. So we have a little bit more aggregate stability. Under no-till also, we see the aggregate stability go up. The organic matter also goes up. So what this tells us is that there is an additive effect. Right? When you combine practices, you get a little bit more bang for your buck. Right? So that's good. That's really good. We didn't know that. Here's another interesting experiment, actually in collaboration with colleagues in North Carolina. Long-term tillage experiment. And we were measuring all of our indicators, but we also had yield measurements. So that's the holy grail, right? If you can relate soil health to yield, that's fantastic. It's very difficult to do. But this is a controlled trial. And what does this tell us? So we had 3 different types of tillage systems, right? Moldboard plowing, most intense, minimum till, mostly no-till, and then chisel being in between. This picture here tells us that as we reduce the tillage, we see higher protein levels. Protein goes up as we reduce tillage. We also see that as we reduce tillage, the protein level goes up and the yield level also goes up. So we can relate tillage to protein to yield. So this is great, right? We can now actually say something about if you reduce your tillage, you make your soil healthier, in this case just looking at protein, and it impacts the yield positively as well. The next slide, I have the same graph, but now for 8 other indicators, or 7 other, 8 total. And I ranked them by how good the correlation was between the indicator and yield. So protein had the best correlation, then active carbon, and manganese, then respiration, aggregate stability, phosphorus, magnesium, organic matter. So note here that organic matter had a relatively weak correlation with yield. But the quality of the organic matter, protein, active carbon, had a much better correlation with yield. Right? So it indicates that these biological properties are more correlated with yield than the total organic matter. Right? And respiration is also one of those indicators of the biological activity. Aggregate stability is strongly impacted by that as well. So we can see that these biological properties are very important. Now you might ask, how about manganese? Why is manganese so well correlated? It's kind of wonky, I should say, but manganese is involved in the cycling of organic matter in the soil. It's a manganese 2+ versus 3+, for those of you who remember your chemistry. Okay, so very interesting that we're finding these patterns and good correlations with yield. All right, now last topic here is coming back to New York. So Joseph and I have been working, and I should say give Joseph most of the credit for doing the work, to look and see to what extent do these different cropping systems have an impact on soil health, specifically for New York. And we had enough data in our soil health database, we had analyzed enough samples, that we could actually say something about that. So we're comparing the texture of the soil, like the medium texture, the silt loam, the loam, the coarse textures like the sandy soils, and the fine texture, the clay soils. And we're contrasting those, and we're also looking at these 5 different cropping systems: dairy, pasture, mixed vegetable, processed vegetable, and annual crops. So just to clarify, mixed vegetables tends to be associated with the smaller organic farms. Okay, processing vegetables are typically larger vegetable farms. Annual crop beans, typically corn and soybean, wheat maybe, but not really any livestock involved as far as we know. All right, so let's first look to what extent does texture, which is the natural variation in the soil. You know, this is a silt loam, that's a clay loam, that's a loamy sand. To what extent does it impact our properties? So let's look first at soil organic matter. And we see that a coarse textured soil, a sandier soil, naturally has much less organic matter than a fine textured soil. Because a fine textured soil has more clay and can bond more carbon and nutrients. Right, so that's naturally the case. So if you have a sandy soil with an organic matter content of say 3, that's really good. But if you have a clay soil with an organic matter of 3, well, that's really below average. Okay, so that we need to keep that in mind. It's the same for these other indicators: active carbon, protein, respiration. We see that the sandier, coarser soils are different than the fine textured soil. Okay, that's maybe nothing new, right? Most of us knew that. Now let's look at what's the impact of how we manage that soil. Right? Notably, what kind of a cropping system is that in? So Joseph used the crop code that was part of the submission form to identify what the different systems were, right? So if it was corn silage or alfalfa, etc., it would be assumed part of a dairy system. If it was corn for grain, soybean, or wheat, it would be an annual cropping system. So that way we could kind of compare. And so let's look at those numbers. So again, first let's look at soil organic matter. So processing vegetables on the average had 2.7% organic matter. Annual crops, corn, soybean, wheat, a little bit higher. You know, the soil is not as intensively used. Dairy systems had quite a bit higher organic matter. Why is that? Because there's manure being applied. There's more cycling of carbon and nutrients. These mixed vegetable systems, a lot of them are organic, a lot of them bring compost onto their land, again higher. And the highest was pastures. Pastures, of course, animals, so there's cycling of carbon and nutrients, and there's no tillage going on in pastures. Right, so those have the highest values. And that basically was the same for all these other indicators, okay? Aggregate stability was quite pronounced. Look here, processing vegetables, only 27% aggregate stability, but the pasture, 70%. Huge difference, right? So here you can see that. This is the different cropping systems, and this is the range of measured values for aggregate stability. Look at this, pastures way above everything else because there was no tillage, right? So tillage destroys aggregates, and we can see that. The interesting thing is that a lot of these pastures in New York were conventionally considered the most marginal soils. I mean, we're not putting land in the Schoharie Valley or the Genesee Valley into pasture generally. Okay, that's too good. You know, you want to grow crops. So a lot of this is hillsides, but it does really make the soil quite a bit better. Okay, mixed vegetables have the largest range of organic matter. So some of them probably have lots of organic matter because a lot of compost was applied. Some of them maybe not quite as much. All right. So we're learning a lot about what's the impact of these cropping systems. I'll maybe skip this one. This is the protein. So let's put together the natural soil variation, which is here texture. So is it a silt loam, is it a loamy sand or whatever, and combine that with the effects of how the soil is managed as part of the cropping system. Is it dairy? Is it cash grain? Is it processing vegetable? Right? And so there's a little statistical trick that we call variance component analysis. but it basically looks at how much of total variability can be assigned to texture class. So for organic matter, 19% of the variability from texture, we can say, variability in organic matter is related to texture. Okay, for active carbon, it's 9%. For organic matter, the same amount of variability is related to cropping system. So a dairy versus a cash grain. When we look, so organic matter and active carbon, it's about the same, the natural variability versus the cropping system variability, human variability. For protein, respiration, and agrostability, most of what we see in terms of differences in the landscape is associated with the cropping system. Not as much related to the natural variability in texture. So for these indicators, it's very strongly influenced by how you manage the soil. Okay? And then available water capacity, which is how well does the soil work as a sponge, most of it is related to texture. A clay loam soil can hold more water than a loamy sand soil. And it doesn't really matter that much how you manage it. Okay? So these properties are influenced in different ways, but the human management, the cropping system, we didn't even look whether it was no-till or plowing, the cropping system itself, and whether you recycle the carbon and nutrients or you remove most of it through crop harvest, has a huge impact. Okay? So those are some very interesting insights. The other thing that Joseph and I decided to work on is let's say, well, what is really a good goal for an indicator like, let's say, aggregate stability, which is WAS here, or protein? What should be a value you should aspire for? And then because we know sort of the range of values that we've observed over the past years from many samples, we can say that if you're in an annual cropping system, say corn, soybean, wheat, a good aspirational goal would be to have 3.2% organic matter. If you're below that, you should try to get to that level. If you're above it, you're golden. Okay? But if you're below this value, we know that many farmers are able to achieve that. And so you should be able to achieve that value. Now this is for loam soils, by the way. We have it for different texture ones. The protein value, for example, 5.4. That is a good goal to have. If you get a soil health test report and you're below the 5.4, you should think about it would be good for the health of your soil to try to get up to that level. Right? So it's a little bit like your blood pressure. If your blood pressure is above 120/80, then your goal should be to get to 120/80. Right? Try to get that down, whichever way you want to do this. But this is really very important in our view because we have established standards for air quality and water quality, other indicators, but we didn't have anything for soil health. No soil quality indicators. So this is a first attempt, based on the data that we have, we say, let's put some numbers to this. Like your blood pressure, 120/80. Okay? Let's put some numbers to it. So this is where we are. So we're kind of excited about that. And you can see that, if you're in say processing vegetable system, you're inherently in a much more challenging situation. So 3.1% organic matter is maybe good. Whoa. It's good to be close to the screen. Yeah, maybe this is like Vanna White, right? My assistant here. Thank you. I think you better stay close. I'm just about done. So the other thing that people are very excited about is carbon farming. How many of you have heard of carbon farming, right? And so there's a lot of interest in New York. So the idea is that we have too much carbon in the atmosphere as carbon dioxide, to try to get that into the soil and to maybe pay farmers for that. What we need to keep in mind is that our soils are already at different levels of carbon. As I just said, a dairy farm or a mixed processing operation already has more carbon than, say, a cash grain operation. So the way we can look at it is that some soils are very depleted in carbon, and they could accept more carbon. The glass is empty, you can put more into it. And there are other soils that are maybe already full of carbon. You can't really add any more carbon. The storage capacity of the soil is already at full capacity. Okay, so the glass is already full. So the idea that I think we should think about, especially in New York, is, well, maybe these areas where we have already the glass full, we already have carbon saturation, maybe some of that carbon could maybe go to some of these areas that are empty or that are carbon starved, right? So in New York, I think we have a huge opportunity because we have a very diverse agricultural system. Here are the CAFOs in New York, a map from the DEC, large and medium-sized CAFOs. These farms tend to already have quite a bit of carbon and nutrients. In some cases, too much, right? And they're often interspersed with processing vegetables or cash grain operations. You know, they're not. It's not like we have one area where all the dairy farms are, although Wyoming County has an awful lot. But you go to Cayuga County, you see dairy farms and you see cash grain operations, and there's a huge opportunity to share some of that carbon and the nutrients, because the dairy farms are already mostly saturated with carbon. You can't do any carbon farming if the glass is already full. You can't really put any more into it, right? So Joseph did some analysis where we say there's an equation that basically tells you what the carbon saturation level is in the soil. And so it's 100% here, that's the red line. And we see that some of these operations, like most of the pasture land, is already at 100% or maybe above, or at least maybe 40%. So that means that you can't really do any carbon farming there because it's already at the saturation level, right? A lot of the mixed vegetable farms, a minority, but still a significant number, they've gotten a lot of compost and all that, they're already at the saturation level, right? But most of the annual crops and processing vegetables are well below the saturation level. So those farms, those lands, those soils would really benefit from the carbon and the nutrients, right? It allows carbon storage and makes the health of the soil better, right? So I think that New York has a huge opportunity to move some of this carbon and nutrients from one place to another, because we have all these different farms more or less interspersed. Okay, in conclusion then, anthropogenic, human spatial processes are increasingly influencing soil properties, right? So you can take a soil map of whatever, Seneca County, and you can look at what the soil properties are, and you can say, yeah, this is a clay loam and all that, but what's becoming increasingly important is that field also part of a dairy farm, is a part of a mixed processing, a vegetable farm, is a part of a cash grain operation. Because the soil properties will be different as a result of the operation and the management, okay? Soil health assessment gives us some really interesting insights. I think we're learning a tremendous amount. Cropping systems appear to have a big influence, and I think New York has some fairly unique opportunities to improve the carbon and the nutrient situation in the soil health on all of the farms in New York by doing some spatial reallocation. Can we develop a manure exchange that uses that manure more efficiently? Can we get it off some of the dairy farms where it's becoming a problem and the soils are already saturated? Can we get it onto some other farms that could really use the carbon and the nutrients? So with that, I'll hand it back. Thank you.
We have some time for questions. If anyone has any questions, you could probably take 2 or 3.
Could you comment possibly on, you said that, combining, obviously, I think it was less tillage and cover cropping sort of added to the benefit of
Right.
soil health. Comment maybe a little bit on adding in contour planting? You guys studied that really well?
Contour planting has a positive impact. So the way you can look at sort of the soil health, there are practices that improve the soil health, and there are practices that decrease the soil health. So if you don't do contour planting, you have a higher potential for erosion, which means that you're removing, you know, some of the best soil right from the top. So if you do contour planting, yes, that would be beneficial. I can't give you any numbers on how contour planting combined with cover cropping, combined with, say, reduced tillage, whether that has an additive effect. As a scientist, I would feel fairly confident to say yes. I think that's, you know, it appears that if you combine good practices, you get more benefits. And it's a good practice, yeah.
So in those carbon saturated soils, where does the excess carbon go? Does it,
So most of it basically gets recycled back into the atmosphere. So, you know, think of a soil as a sponge, right? A sponge for water, but also a sponge for carbon. So when you saturate a sponge, then that water comes out, right? So the sponge has a limited capacity to store that water, and that means that it just kind of leaches, you know, or drains out. Same with carbon, it's just that the drainage, the loss of the carbon is basically into the atmosphere, because the carbon is held in the soil by basically attaching itself to the mineral particles. That's why if you have a lot of clay in your soil, you can store more carbon. If you are at the 100% level, then it cannot store that carbon, so the biological activity basically then decomposes that and goes back into the atmosphere. So you don't have any net gains. If you have a soil that is very low in carbon and organic matter, and it's below the maximum storage capacity, it's like a dry soil that gets a lot of rain, it can store that rain, right? So it's the same concept. So I think that the main message here is that when we think about carbon farming, we need to sort of put that in the context of what's already there. You know, should a farmer get, say, payments for doing carbon farming when their land already is saturated with carbon? I mean, that's up to the politicians to decide. Yeah.
so eventually a CAFO might be regulating that carbon too.
I wouldn't promote necessarily regulation in the early stages, but I think that, and we're starting to do some work at Cornell, is to sort of evaluating where that carbon is and what would it take to move that carbon, say in Cayuga County as an example. What would it take to move some of that manure from this dairy farm to a cash grain operation that's maybe 3 miles down the road? What would the cost of that be? Because we're not really accounting for the benefits of doing that. Right now, most of the farms are relatively insular. Not that there's no movement of manure going around. I know that there is, but it's not in a systematic way. But let's say, take Cayuga County. What would it take to move some of that manure from the excess nutrients and carbon from this dairy operation to a nearby cash grain? And what would be the monetary benefits? What would be the cost of doing that? What would be the benefit to the cash grain operation? How much is that farmer willing to pay for that? And I think that's the way we need to start thinking. And can we then turn that into also carbon credits? Right, so if there is a carbon market, then we can bring that into it as well. I hope that people in Albany are becoming a little bit more sophisticated about this issue. I think it's, carbon farming currently is a slogan, but I think we need to have a little bit more nuanced approach to it. But we'll get there, we'll get there. Any more questions?
Is there a maximum, you talk about soil that's low in carbon and high in carbon. Are there properties of the soil that will keep it from absorbing anymore, even though it's low in carbon?
Right, yeah, there is. Let me see, it's right here at the bottom. It basically has to do with the amount of clay and silt in the soil.
Right, the makeup of the soil.
The makeup-
might keep it from absorbing.
Right, right. So if you have a sandy soil, like on Long Island, right, its ability to absorb carbon is quite limited. If you have a clay loam soil, like right here, right outside this shed, pretty heavy soil, it can absorb a lot more carbon. You know, it's like, you know, is it a person who is 5'2", how many calories do they need versus a basketball player who is, you know, 7 feet tall? Their ability to process more calories is greater. So not all soils are created equal in that respect. So we need to, you know, we need to start looking at it. We shouldn't just say, okay, if you just change your practice, you should get payments for carbon farming. It needs to be in the context of what's the soil type, how much carbon is already there, and then you can think in terms of payment. I personally believe that it's a huge win-win. You know, it's not only about that you can store the carbon in the soil, but you can make the health of the soil better as well, right? So why aren't we doing this, right? I mean, that's basically where I am at this point in time. It's such a great opportunity, especially for this state. If you were in Iowa or Indiana, where you have just a lot of cash grain operations, you have livestock-based stuff as well, but that potential is maybe a little bit lower. But here it's so interspersed, you know, that the livestock and the cash grain and processing vegetable operations that would really benefit from the carbon from the manure. And you had a question as well?
Could you speak to cultivation in organic crop operations? Seems to destroy soil structure and such, but you need to cultivate to get rid of the weeds. Are there ways to optimize the effects of cultivation, the different timing tools, depths?
Yeah, so in terms of organic farms, so a lot of them, you know, have naturally better soil health because they have to do certain practices, because otherwise you can't grow organically. So one of them is typically rotation with legumes to get the nitrogen, to break the disease cycles and all that. So there's typically less tillage going on during those phases, right? But when they do grow their main crops, then they have to typically plow. There's some people who do some no-till organic, but it's very difficult. It's very cutting edge, and so there typically is a lot of tillage going on. The tillage that's most damaging is the more intensive tillage, like a mow or plowing. Using a tine cultivator, where you just kind of scratch the surface, is not nearly as damaging. But organic farms, they benefit from, you know, manure, compost, whatever, organic sources of carbon and nutrients, and the rotations, but the negative side is that there's typically more tillage. So in a way, you know, they have different pluses and minuses, different practices that either benefit or are detrimental to soil health than, say, a traditional corn and soybean operation, okay, where you don't naturally have as much carbon coming into the system. A lot of it gets exported off the farm, but they maybe are using strip till or no-till. So they're reducing the negative effects, and but they also have less of the beneficial practices. So that's why in a system like that, so if you're in a cash grain operation, you naturally are fighting against a system that, you know, exports most carbon and nutrients. So it's even more important to reduce tillage, to bring in cover crops, to find sources of manure or compost, because it's more beneficial there.
Awesome. Well, thank you.